Okay, welcome to today's lecture. We're going to talk about the dot product, its properties, orthogonal vectors, and in general, the angle between two vectors. And we're going to look at the projection of a vector onto another vector and how that is used in different contexts. So let's begin with the dot product of two vectors. We're going to provide two definitions for the dot product of two vectors. So first of all, let's start with a notation. So the dot product of two vectors u comma v is a real number that will be denoted by u dot v. This is a case where, unlike multiplication of real numbers, we usually do not skip that dot between the vectors. And what is interesting here is that we combine two vectors and get one number. I'm going to give two definitions of this. The first definition is going to be rather revealing about what the dot product is, but it's going to be, as you're going to see, we're going to have a major hurdle in applying that definition. The second definition is not going to provide us with any intuition about the dot product, but it will be a breeze as far as computations are concerned, and that will be the definition that we're going to be using. So the first way of describing the dot product between two vectors is that it's like this. You start with two vectors and you force them to originate at the same point. We've seen this before. And as long as the two vectors are non-zero, there are two angles that are being formed by these two vectors. Usually one will be smaller than the other. There is, of course, the case where the two vectors are parallel and point to opposite directions in which both angles are equal to pi. We're going to be using radians from now on, so I'm not going to say 180 degrees, I'm going to say pi. We have a small problem here is if one vector is the zero vector, then we don't really get an angle. But as you're going to see in that case, you can take any angle to pretty much be the angle between the two vectors. So let me call this angle theta. So basically the understanding is that theta is between 0 and pi. Okay, and the dot product between the two vectors is defined by the magnitude of u times the magnitude of v sorry about this, there was a little dot there, times the magnitude of v times the cosine of the angle between the two vectors. Okay, so this is the dot product of the two vectors, and you can see right away that it depends on the magnitudes of the two vectors, but also on the relative position. So for example, you may have two huge vectors, huge magnitudes. If they happen to be orthogonal, then the dot product is actually 0. Okay, and of course the dot product is maximized if the two vectors are parallel and point to the same direction. I'm going to come back to these comparisons very soon. So let me leave the definition at that for the moment being, and let me give you the other definition. The other definition is completely algebraic in nature. So let's say that we are in 2 dimensions, and the first vector has coordinates u1, u2, and the second vector has coordinates v1 and v2, and then their dot product is simply u1 v1 plus u2 v2. See how now that I'm dealing with real numbers, I'm skipping the little dot, so u1 times v1 is denoted simply as U1 and V1 just juxtaposed to next to each other. And you can guess what it's going to be in 3 dimensions. I could give you the definition for the 3 dimensions as a little exercise here. So can you guess? So if you have the vector U1, U2, U3, those are its coordinates, components if you like, and V1, V2, V3, then U dot V would be what? Please pause the recording and try to figure out for yourselves the definition of U dot V. And I'm going to write it down now. It's going to be U1 V1 plus U2 V2 plus U3 V3. Believe it or not, these seemingly irrelevant to each other definitions actually give you the same result. Again, we're going to take advantage of this. Again, the first definition reveals a lot about the nature of the dot product, but the second definition makes it very easy for us, especially since we're going to be constantly working with coordinates to compute the dot product. So I suggest that we actually do a couple of examples. So let's say that we have that U is equal to 1, -5, and V is equal to 2, 2. Find U dot V. And also if U is equal to 1, 3, -2, and V is equal to 2, 1, -1, find U dot V. Also, let me give you a little exercise in this first setup. So let U comma V be unit vectors that form an angle of pi over 6. Same thing as 30 degrees. So what is U dot V in this case? Okay, please pause the video for a few minutes. Try to find the answers to these 3 questions. I'll give a couple of seconds for the recording, and then you can see what the answers are. Okay, so for the first one, we will have 1 times 2 plus -5 times 2, which is 2 minus 10, also known as -8. Okay, for the second one, we will have 1 times 2 plus 3 times 1 plus -2 times -1, and that would be 7. For the case where we're using the first definition, since they're unit vectors, we will have the length of U is 1, the length of V is also 1, and the cosine of pi over 6 is square root of 3 over 2. So the final answer is square root of 3 over 2. And that's our first computations of the dot product. So at this point, we should actually mention one of the interpretations of the dot product. So imagine that you're looking at, actually, whenever I teach this in class, I like to do this demonstration, that you have a table and you want to push the table, right? And you're actually putting a force. If you're, if you do it routinely without paying too much attention, let's say that your force applies this way and the table is pushed that way, then the dot product of the vector that gives the displacement of the table with the vector that gives the force of the table actually provides you with the work that is being produced here. And you can see that that work is going to be the magnitude of the two vectors times the cosine of the angle. So simply speaking, if you wish to maximize the work that you're producing, then it's a much better idea to push the table in a way which is parallel to the ground. So this way you align the two vectors become parallel, and you actually maximize the work that you produce. And if you perform this experiment, this actual experiment, then you're going to see that it becomes much easier if you put the same amount of force and you align your hands, your arms with the ground, you push in a way that the force is applied in a parallel way to the ground, to the displacement, in other words, of the table, you can see that you don't, that everything appears to be much more effortless. So let's now state the properties of the dot product. So first of all, the dot product behaves very, very nicely when it comes down to the vector operations. So to make our life easier, let's begin by noticing that the dot product is commutative, meaning the order in which you take the two vectors does not really matter. Okay. And once we have noticed that, then we can argue that it behaves very nicely when you consider it by fixing one of the two components of the dot product. So for example, if I take u with the sum of two vectors, the dot product with the sum of two vectors, then there is a very nice distribution of the dot product. So it's u dot v1 plus u dot v2. And you could have done this on the first coordinate or on the second coordinate. That's the significance of saying that the order in which you take the dot product doesn't really matter. And if you take the dot product with a scalar multiple of a vector, then that will be the scalar multiple, the same scalar multiple of the corresponding dot product. Okay. And this pretty much these properties imply, these three properties imply, the first one is not really needed. I mean, even though it helps things out, but the dot product is bilinear, as we say. So it's linear with respect to each of the two components. Again, by definition, if you have something, a function which is bilinear, then it doesn't have to be commutative, but in our case, the commutativity helps us to write the bilinearity in a much simpler way. Then the dot product of a vector with itself is always greater than or equal to 0. Of course, I mean, think about it. If you have u is, let's say, the vector u1, u2, then what is u dot u? U dot u will be u1 squared plus u2 squared. And the only way that this can be, that this is 0, is if actually the vector itself is the 0 vector. In fact, the dot product of a vector by itself is intimately connected to the magnitude of a vector. It happens to be equal to the square root. So the magnitude of the vector is the square root of the dot product of the vector with itself. And of course, you could write this as the dot product of a vector by itself, with itself, is equal to the square of the magnitude. These two relations are obviously equivalent, but we can use either one of them. Now, the dot product between two vectors has the same sign as the cosine of the angle between them. And the cosine of an angle is positive if the angle is acute and negative if the angle is obtuse. And it's zero if the angle is a right angle. As I said, we don't really bother with an angle between a vector and the zero vector. So imagine that you have two non-zero vectors. Then, and let theta be the angle between them. Then theta is acute if and only if the dot product between the two vectors is greater than zero. Theta is right, meaning the two vectors are orthogonal if the dot product between them is zero. In this case, we write that U is orthogonal to V. So we use this little very nice notation. And finally, theta is obtuse if and only if the dot product is less than zero. Okay, so the dot product between two non-zero vectors gives us immediate information about the kind of angle that we have between the two vectors. In fact, we can argue by using the first definition that the cosine of the angle between two vectors is simply u dot v over the length of the product of the length of the magnitudes. Okay. So you might argue here that if you use the inverse cosine, the arc cosine as I like to call it, this will be the arc cosine of u dot v over the magnitude of u times the magnitude of v. And you can use this formula along with a calculator in order to find the angle between two vectors. In some sense, if you have the cosine of an angle and you know that the angle is between 0 and pi, that is pretty much the same as having the cosine of the angle. So the cosine or the angle itself should be considered the same piece of information. The other property is what we mentioned in passing, that the dot product can never exceed the product of the magnitudes, because if you look at the first definition, it's the product of the magnitudes times cosine, which is an angle between 1 and -1. And by the same token, it can never be less than the opposite of the product of the magnitudes. In fact, any of the two equalities occurs if and only if the two vectors are parallel. Okay. Then we have another very, very nice property. If you have two vectors that are orthogonal to each other, again, I'm assuming they're non-zero vectors, then the square of the magnitude of the sum of the two vectors is equal to the sum of the squares of the magnitudes. And there is a very simple reason why I'm mentioning this. It's not all that important. I mean, it's not like a property of the dot product that by itself stands out. It's just that this is none other than the Pythagorean theorem. And in fact, it's quite instructive to see how we actually obtain this. So imagine that U is orthogonal to V, which of course translates to U dot V being equal to 0. Then take U plus magnitude, take magnitude of U plus V squared. By the property that says that you can link the square of the magnitude with the dot square of the vector, this is immediately the dot product between U plus V and itself. And now you can apply the distributivity of the dot product. So this is U plus V dot U plus U plus V dot V. So in other words, I'm considering this as one vector, and then I take the product with this vector and that vector, and now I distribute once more, and this gives me U dot U plus V dot U plus U dot V plus V dot V. And of course, we said that the vectors are orthogonal to each other. So this is 0, this is 0. And now the two remaining vectors can be written as magnitude of U squared plus magnitude of V squared. I'm sorry, the remaining two dot products can be written as the squares of the magnitudes. Again, exactly because that's how the magnitude is connected to the dot square of a vector. Okay, so we have this very, very nice property. And the last thing that I would like to do is talk about the projection of a vector onto another vector. So here's how this is done. Imagine that you have a vector U, and you also have a vector V. Again, without loss of generality, we can assume that the two vectors originate at the same point. You will see that that is not even needed that much. So what you do is you project the vector U onto V. And the vector that you receive this way is called the projection onto V of the vector U, or rather the projection of U onto the vector V. So this is going to be, by definition, parallel to the vector V. And the truth is that knowledge of the vector V is not even required here. All you need to know is pretty much a line which is parallel to the vector V, and you can do that projection. I mean, think about it. If I know a line which is parallel to the vector V, I just make vector U originate anywhere on that line, and then I simply project it, and I get the vector that you just saw. Okay, but there is a very nice formula for this vector, and the formula is as follows. The projection onto V of U is U dot V. This is a number, right? Over V dot V. Don't fall in the trap of thinking that you can do a cancellation here. A cancellation is done with numbers. It's not done when you have dot products of vectors, right? It wouldn't even make sense, because if you try to cancel V and V, you would get a quotient of two vectors. That hasn't even been defined. I mean, we haven't said what the quotient of two vectors would ever be. But in any case, once you find that number, then as the quotient of these two numbers, then you scale the vector V by that number. And that's the formula of the projection. Okay, so let's do an example. So let's say that U is 1, 3, negative 1, and V is 1, 1, 1. Then the projection onto V of U is going to be the dot product of 1, 3, negative 1 with the vector 1, 1, 1 divided by the dot product of the vector 1, 1, 1 with the vector 1, 1, 1. And you have to scale the vector 1, 1, 1 by that quotient. So let's begin by finding that quotient. The numerator is going to be what? 3. The denominator is again equal to 3. So, and the vector happens to be, it's a very interesting case, it happens to be just 1, 1, 1, the vector itself. Okay. Now there's something else which is very, very interesting here. It is that if you take the vector and you subtract from it its projection onto the vector V, then this is going to be perpendicular to the vector V. I think a picture here will elucidate what I'm trying to say. So basically the picture looks like this. Let me do it right here. So let's say this is the vector U, and this is the vector V. And this is the projection of the vector U onto the vector V. And now the U minus the projection is going to be precisely this vector right here. So this is going to be U minus the projection onto V of U. And you can see that pretty much the vector U is written as the sum of these two vectors, the blue one and the red one. And so let me demonstrate this right here. So basically I'm saying that the vector U is written as the projection onto V of U plus U minus that projection. It's almost as if you add and subtract the projection, right? And then what happens is that this vector right here is parallel to V. And this vector right here is orthogonal to V. And of course, what you're going to have is that exactly because they're orthogonal to each other, you will have that the magnitude of U breaks into the magnitude of the projection squared plus the magnitude of U minus that projection, also squared. Okay. Let's look at the specific vectors that we had. So if we take in our example, I remind you that in our example, we had that U was 1, 3, negative 1, and V was 1, 1, 1. And we found the projection on U onto V to be actually the vector V, 1, 1, 1. Then U minus the projection is going to be 1, 3, negative 1 minus 1, 1, 1, which gives us, of course, 0, 2, and negative 2. So you can see now that the vector 1, 3, negative 1 is written as 1, 1, 1 plus the vector 0, 2, negative 2. And of course, here the idea is that this vector is parallel to 1, 1, 1. Actually, it coincides with 1, 1, 1 to be more precise. And this vector is orthogonal to 1, 1, 1. And such a decomposition of the vector into these orthogonal components is something that physicists do all the time. So they have a motion, they want to simplify the study of that motion, they analyze it on two axes where they can consider the forces independently of each other and pretty much understand very well how the motion takes place on each axis. Then they put together the two component motions and they come up with the actual motion in the number of dimensions where it is being where it takes place. And with this, our lecture comes to its end. Thank you for watching.